In this video, we're going to look at specific stage 2 metabolic pathways. And the first one we'll look at is glycolysis. So how we break down carbohydrates to form acetyl-CoA. Now, glycolysis comes from glucose. The glyco is for glucose. And then the lysis is to break. So we're talking about breaking glucose, right? And this is a very linear pathway. So we'll take a look at glycolysis overall, but this is not cyclic like the Krebs cycle. This one is really linear. So in this one, we've got C6H12O6, or our glucose, is going to get oxidized, and it's going to react with 2 NAD+, and NAD+ is going to be reduced. So NAD+ is really, it's currently in its oxidized form. And so that's going to be reduced. It's going to net to ATP. So 2 ADP are going to net to ATP overall from glycolysis. And then it's going to produce 2 molecules of pyruvate, CH3, C double bond O, COO minus, or C, double bond O, and then an O minus. So, and then it's going to form 2 NADH. Now, this is the reduced form of the coenzyme. The NADH is the reduced form of the coenzyme. That's going to get carried forward and used in stage 4. And then it will also form 2H+, or 2 protons. So this is how we're going to break down glucose in this very linear pathway to make the NADH that we're going to use in stage 4 and to make pyruvate. Okay, so we said glycolysis was, about glucose, and lysis, or breaking. So breaking glucose in this linear pathway. Now this graphic just kind of shows that linear pathway. We don't really need to know that, but I can describe it to you just so we kind of know the big picture. It says in step 1, glucose reacts to form glucose 6-phosphate, and ATP is converted to ADP. So you can tell that we've lost a phosphate and given it, to that glucose molecule, essentially. In step 2, we use phosphoglucoisomerase to convert the glucose 6-phosphate into fructose 6-phosphate. In step 3, we use phosphofructokinase to convert ATP to ADP. That one's a tongue twister for me. And then the fructose 6-phosphate goes to fructose 1,6-biphosphate. Then we use aldolase in step 4 and convert that to dihydroxyacetone or to 2 glyceride and 3 phosphates. Now there can also be a step 5 that takes the dihydroxyacetone phosphate and uses another enzyme, which I equally can't pronounce, to make the 2 glyceride and 3 phosphates. Step 6 takes glyceraldehyde 3-phosphate dihydrogenase to convert the 2 glyceraldehyde to 2,1,3-biphosphate glycerates. And in that step, NAD+ and 2 phosphates are converted to NADH and 2H+. And then we've got 2,1,3-biphosphoglycerates. And then in step 7, phosphoglycerokinase, it converts 2 ADP to 2 ATP. And the 2,1,3-biphosphoglycerates are converted to 3 phosphoglycerates. Step 8 converts them to 2 phosphoglycerates, to 2 phosphoglycerates, rather. And that uses another enzyme. And then there's another enzyme in step 9 where we lose 2 waters and get 2 phosphonyl pyruvates, and then pyruvate kinase in the last step 10 to make 2 pyruvates. And in that step, 2 ADP is converted to 2 ATP. Okay, so we're forming some ATP in there. What's the big picture? Do we need to know all this? Not really. I mean, really, let's know that glucose starts off with its 6 carbon atoms, and that in the end, you make 2 pyruvates. They each have 3 carbon atoms, so that's where the carbons go. You're breaking that 6 carbon glucose into 2 pyruvate molecules that each have 3 carbon atoms. This is a really linear step-by-step process. It's not cyclic. We're not regenerating and sending something back into the cycle. Excuse me. And so, this is the way that sugars and starches that were, digested by hydrolysis in step 1 to form glucose, go on in stage 2 to make pyruvate. So maybe I'll just write that down. We would have had sugars and starches, and in stage 1, digestion, and hydrolysis, they would have been converted to glucose. Again, that's stage 1. That was about digesting these. That's usually hydrolysis to break it apart into individual glucose monomers. And then that glucose is going through stage 2. So this glycolysis, this is all of our big stage 2 pathway just for glucose. So this is what we're talking about when we say it's a really specific pathway. Do you have to know the whole pathway? No, but it's good to know that it's linear, that it takes your 6 carbon glucose and makes 2 3 carbon pyruvates. Okay, so the next question is, then what happens to the pyruvate formed in glycolysis? It depends on the conditions. That's the big takeaway, that this is going to be very condition dependent. It depends on if we have oxygen available or not. So aerobic conditions are what we, call it when we have oxygen. So with oxygen, these are going to be aerobic conditions. In these conditions, we'll have pyruvate, and the pyruvate itself gets oxidized. And pyruvate's going to be broken really in half, right? We're going to break the CC bond in the middle so that we get the CH3 C double bond O on one side. And then we break the CC bond and get the C double bond O and the C bonded to O minus on the other side. So it's kind of mirror image, just not the exact same thing on both sides. And then we have CoA. So it reacts with enzyme CoA. So that's your thio-CoA, your HS-CoA. And NAD plus actually gets reduced to NADH and H plus, and you make acetyl-CoA and CO2. So, the C double bond O side of the pyruvate really becomes CO2, and the 2 carbons on the pyruvate, well, they're going to get shuttled on acetyl-CoA. So the CH3CO, C double bond O, that becomes your CH3 C double bond O on your acetyl-CoA. So the one side of pyruvate was really going to get shuttled as acetyl-CoA or C2, and the other side of the pyruvate molecule is really released as carbon dioxide. Okay, so NAD plus gets reduced to NADH, pyruvate gets oxidized to acetyl-CoA, and that will go on to stage 3, right? These acetyl-CoA is all ready now for stage 3. What about anaerobic conditions? This is if there's low or no oxygen present. If there's low or no oxygen present, it's important to note that in electron transport, NADH, the reduced form, is supposed to react with oxygen to get oxidized to NAD+, in stage 4, in electron transport. So we already learned about electron transport. That's supposed to be happening in stage 4. But if you don't have any oxygen present, then you can't properly make NAD+. So in a lack of oxygen, in an oxygen-deprived environment, So say an athlete's really, exerting themselves and not getting enough oxygen, they won't have that NAD plus. So what happens instead is NADH has to get oxidized to NAD plus. Well, how is that going to happen? Well, that's going to happen with pyruvate, but instead of pyruvate getting oxidized, pyruvate actually has to get reduced, right? So pyruvate needs to get reduced. So the C double bond O in pyruvate in the C2 part of it. So we've got CH3, C double bond O. Then we've got it bonded to a C double bond O, and that C is bonded to an O minus. Well, it's the CH3, C double bond O. That's going to change to CH3COH. And so that's where it gets reduced. It's being reduced, from a ketone to, oops, put an E on ketone, to a secondary alcohol and lactate. Okay, so if we're without oxygen, oh, let's maybe erase, oops. So without oxygen, electron transport, the whole electron transport chain and oxidative phosphorylation essentially just gets stalled out. No oxygen, no stage 4 formation of NAD+. So then what happens is pyruvate ends up getting reduced so that NADH can get oxidized. Pyruvate itself gets reduced to OH, and there's lactate buildup, and lactic acid buildup will cause runners and athletes to get cramps, and essentially they need more oxygen. So sometimes breathing deeply can help, just sort of resting and getting a lot of resting deep breaths can help, but essentially they've just got a buildup of way too much lactic acid. Okay, just to sort of recap, the big picture idea here is that glucose is converted to pyruvate in stage 2 metabolism. Every glucose molecule is actually converted to, to two pyruvate molecules. And then what happens to those pyruvate molecules really depends on if you have anaerobic conditions without any oxygen, or if you have aerobic conditions, and those are conditions with oxygen. So without oxygen, you can have reduction in skeletal muscle, like we were talking about, to make lactic acid or lactate. And that really gives runners cramps and things. And that's because you don't have any oxygen present to form NAD plus in stage 4 metabolism. So if you don't have any NAD plus, then NADH has to be oxidized to NAD plus actually by the pyruvate to make lactic acid. So that's what happens in muscle. Actually, though, in yeast, it's called fermentation, right? So when sugars ferment, they actually form ethanol without oxygen, and that ethanol is that beverage grade alcohol, that makes wine and beer alcoholic. So that's formed from fermentation of sugars with yeast to make alcohol. So without oxygen, anaerobic, we're talking about sugars to make ethanol. With yeast, we're talking about the production of lactic acid in muscles when we don't get enough oxygen. Now, with oxygen, we'll be able to use NAD+. We'll have plenty of NAD+ present from stage 4 of electron transport. That NAD+ can be used to convert pyruvate to acetyl-CoA, and acetyl-CoA can just head straight to the citric acid cycle. So this is what happens just like normal if we have plenty of oxygen present. Then NADH is reduced, and that can go on to stage 4. So that can just be used at stage 4. So everything sort of gets recycled and gets used where it needs to be. The human body is great for that. So that's specific stage 2 just for glycolysis, just for glucose.